During this week, we will be discussing the design for reliability. Already in the previous week, we have referred to several aspects of reliability modeling. Now, during this week, again there will be 5 lecture sessions on reliability. So, let me first tell you what are these topics we are going to cover. During first lecture, we will be referring to again reliability of the systems, and particularly one particular say important subsystems or the systems we will be referring to, that is the systems with standby components. How to improve reliability of a system. So, this you must have several ideas, and these ideas must be you are supposed to use those ideas to improve the reliability of a system as well as the reliability of the component. Now, what are these methods, or what are the approaches with which you can improve the reliability of a system? In lecture 2, I will be discussing reliability and life testing plans. That means the main issue is how to get an estimate of the reliability of a component or a system. So, which procedure you should employ to estimate reliability, and for which many a time we refer to reliability and life testing plans. There are many types of life testing plans. We will be discussing all these plans one by one, and essentially we will be focusing on measurement of reliability using life testing plans assuming exponential distribution, and we will be also referring to the operating characteristic curves like we have for the sampling plans as well as for say the control charts. Okay, so the OC curve is basically represents the performance measures of such a sampling plan, or that is basically a sampling plan, and we in this context we say that is the life testing plans. Lecture 3, lecture 4 and lecture 5. These 3 lecture sessions will be exclusively devoting on solving numerical problems on quality and reliability. So, this is our plan. Now, let me first discuss the first topic, that is the reliability of the systems with standby components, and how to improve reliability of the systems. What do you find that when you talk about a system, now as you are all aware of that the systems may have different kinds of say the configuration. One such configuration is series configuration. The second one, alternative to series, it could be parallel, or in many a time majority of the systems you will have both a series as well as the parallel configurations. Now, what actually you need to do, there are certain systems where that failure is just not acceptable. Okay, and if the failure occurs, there will be serious consequences. Like say suppose say the operation theater as a system. Okay, so suppose the power line goes off, the main line goes off. So, you can well imagine what could be its consequence. So, you have to think of the changing configuration of the system in such a way that even if the main power line fails, then alternative the power lines you must be made available at immediately as quickly as possible. So, when you talk about such a system, what you need to do, that means you must have a standby component. So, in this lecture we will be referring to how to model the reliability for a systems with standby components. Okay. So, This I am going to elaborate. Like in many instances, a system with standby components is preferred in order to have guaranteed performance over time. That means there must be guarantee that come whatever may, the performance has to be assured. So that kind of system you want to develop. So many a time a system with standby components you have to develop. In this case, the failure of the system is not acceptable. This point already I have highlighted. There may be serious or adverse impact if failure occurs. Is it okay? You can identify such systems. They are in plenty. Okay. So what you as a learner, as a student, you must be able to identify those systems where the standby components are included. Okay. A system with standby components is recommended under such circumstances. Okay, so why you do go for the standby components? So that when as a system you allow the redundancy. Is it okay? So we'll be referring to the level of redundancy later on. So in a standby configuration, one or more parallel components take over operation upon failure of the current operating components. Is it okay? I repeat, one or more parallel components. That means you have a basic component, and basic component is linked with one or more parallel components. There could be one the standby, or there could be in general n number of standbys. Okay, depending on the systems you are modeling. So as soon as the basic component fails, so one or more parallel components will take over operation, and then obviously the reliability is assured. Is it okay? So that means the service is available, operation is made available all the time. So that is the guarantee you must provide. Now, in a system with standby components, it is assumed that only one component in parallel configuration is operating at a given time. Is it okay? That means there could be n number of components, but what we are assuming that for the systems to run, at least one component must run. Is it okay? So what is the configuration? You have the basic component, and what you have added, you have standby component, say one standby, second standby, and this way you can add the nth standby components. Is it okay? That means if so there are at any instant of time, even if there are n number of failures, suppose n is 6 or n is 10, that means there is a probability. Okay, the probability could be very less, but still there is a probability that suppose n equals to 10, that means all the 10 units may fail. So the basic component is working, or out of say 11 say the elements you have, suppose n is equals to 10, so out of 11 the components you have in a system, at least one systems must run. Is it okay? So it is a general configuration. A general configuration, if you look at, you will find is a standby system with a basic component, as I already mentioned, and n standby components in parallel. Is it okay? The parallel systems already we have explained, and n could be 1, 2, 3 up to n. Is it okay? Whenever a component fails, operation of a standby component is triggered by a failure sensing mechanism. That means the systems must be made automated. Is it okay? For example, whenever the power from the main line is not available, operation of a diesel generator set is automatically triggered. Is it okay? There are many such the examples you have, okay, where we say that we have created a systems with the standby component. Okay, so now the question is how to measure the reliability of such a system. Is it okay? Now, when we talk about say the determination of reliability of such a system, with standby components. Now you need to assume that the components existing, so at this you are getting the operation from the component, and the component exist in which phase. That means there are three phases I have already mentioned. Like when you talk about the life cycle curve, what you find that initially you have a burn-in phase, then once this phase is over, then you have the useful life phase, and then when the useful life phase is over, then you have actually the wear out phase. Now whenever you try to create a system, make sure that the components are in useful life phase. Is it okay? And if the component is in useful life phase, as far as failure rate is concerned, failure rate is assumed to be constant, and failure rate should be as minimum as possible. Is it okay? So that assumption is valid in the majority of the cases. That means constant the time to failure, say constant the failure rate, that assumption is true, that assumption is valid. So if you assume that the time to failure of a component is exponential, it's a particular case of binomial distribution, binomial density function, with the failure rate lambda. Lambda is assumed to be constant, so the component is in useful life phase, as already mentioned. The number of failures within a time period t is Poisson distributed with parameter lambda t. Is it okay? So Poisson distribution is also a distribution for the discrete random variable, and with a single parameter. So that parameter is lambda t. Is it okay? So there is a proof behind this. Like say, if the that means time to failure of a component, you have to prove it. Is it okay? So this could be one of your assignments. If the time to failure is exponential, right, that means the number of failures within a given time period, say t, is Poisson distributed. That means distribution is Poisson with this parameter lambda t. Is it okay? So this is, you can assume probability that there are x number of failures within time period t is given by this is basically is a Poisson the mass function, that is px, that there will be x number of failures, e to the power minus lambda t to the power x divided by factorial x. Is it okay? When n equals to 1, that means what? That means you have a basic component with one standby, a basic component and one standby component in the system. The system remains operational as long as there is no more than one failure. Is it okay? You have to ensure that the operation is made available at any point in time. Is it okay? So that's why you have proposed a system with standby. Is it okay? So hence the system reliability is given by, that means this is the probability that there will be zero number of failures, and this is the probability that there will be one number of failures. Is it okay? So you have just one standby with one basic component. So either basic component will run, or say the standby component will run in parallel. So obviously the expression for reliability is e to the power minus lambda t plus e to the power minus lambda t into lambda t. You are just applying this formula. Is it okay? That means you are assuming that Poisson probability mass function is valid. Is it clear? Following this logic, we compute reliability of the system for different values of n. As I have mentioned that the value of n may vary from say 1 to n. So for example, when n equals to 2, that means at any point in time, okay, up to 2 number of failures, okay, is allowed. So there are 3 components in parallel, and to run the systems at least one component must run. out of these 3, 1 is basic and 2 are the standby components. So when n equals to 2, what is the expression for r? E to the power minus lambda t plus e to the power minus lambda t into lambda t plus e to the power minus lambda t into lambda t square divided by factorial 2. So when n equals to n, that means in general what will be the expression? This will be your expressions. That means you proceed up to nth term. That means e to the power minus lambda t to the power n divided by factorial n. That means how many components you have in the systems? There is n plus 1, and at least one component must run so that the system can run. This is the condition. So up to n number of failures, okay, you may allow. Is it okay? So what is their probability, right? So this is the probability. So obviously e to the power minus lambda t is common. So the entire expression becomes, that means in series, e to the power minus lambda t into 1 plus lambda t square divided by factorial 2 plus lambda t cube divided by factorial 3, and then you proceed, ultimately you reach the nth term, that is lambda t to the power n divided by factorial n. Is it okay? Now what is the mean time to failure? You know how to compute the mean time to failure, and not only mean time to failure, you also know the basic expression for computing the sigma square or the variance. So is it okay? So here mean time to failure you can compute as n plus 1 divided by lambda. Is it okay? So what is n? That means number of the standby components in the systems. By using a standby configuration, a condition of system redundancy is achieved, thereby increasing reliability of the systems. That means many a time the question is posed that how to improve the reliability of the system. There could be many ways you can improve the reliability of the systems. We'll identify those ways or those methods very soon. One such method with which you can improve the reliability of the system is by adding the system redundancy. Is it okay? So that means you must have the extra protection against failure. Is it okay? So you need to, there could be the different levels of redundancy in the systems, so we'll refer to that. Okay. So as far as redundancy in the system is concerned, there could be the two types of redundancy. The first one is referred to as the high level redundancy, and the second one is the low level redundancy. Now let me explain the two types of redundancy for a system. System redundancy may be obtained by two methods. In the first method, what we do, that means each component comprising the system may have one or more parallel components. Is it okay? That means the extra protection is to be given. That is the first approach. The second one is the entire systems may be placed in parallel with one or more identical systems. That means here in the first case what you are trying to do, that means you are in a system remains same, you are not adding a new system. What you are trying to do, that means against each component in the systems you are adding one more component, one or more components in parallel. Okay. Whereas in the second systems what you are trying to do, that means you add, that means instead of having just one system with a particular component configuration, same configuration. Is it okay? That means another systems with the same component configurations you are adding in series. Is it okay? So this two types of redundancy, okay, you add many a time you do it, and so the first method is known as the low level redundancy. That means you are not adding the same systems. Okay, you are not adding the system. What you are adding? You are adding the component in the system, in the systems. So that is referred to as low level redundancy, whereas the second one is called the high level redundancy. Is it clear? I think it is very, it's well explained and is clearly understood. Now, consider a system comprising two serial components A and B. So, this is component A, this is component B. So, what we are trying to do, that means initially you have these series systems. Now, in order to say add redundancy in the systems, what you have made, that means against a component you have added another this identical component called A, and against B again you have added another component called B, and in the same you have added within the system the same subsystems, that is the series configuration. Is it okay? So, obviously this is with respect to the two components A and B, we are referring to the low level redundancy, that means within the system. Whereas here what you are trying to do, that means the two components in a high level redundancy. Here what this was your system, you have added another systems. Is it okay? So, this is basically high level redundancy. That means these systems will run only when say one of these two will run. And now when you add the system, what will happen? That means one of these the two components will run in the system. So, we added them. So, obviously this is referred to as the high level redundancy with respect to the systems, and this is referred to as the low level redundancy because it is referred to the component level. Is it okay? Now, how to the compute the reliability of the systems when there is a low level redundancy, and similarly how to compute the reliability of the system when there is high level redundancy. So, with respect to these two components, so we have computed, if we assume that both the components have the same reliability R. This is a particular case. Is okay. In general, the component reliability may vary from one component to another, but here for the simplicity, okay, for illustration purpose, what we assume that the component reliabilities are same. Then the system reliability for the case of low level redundancy is given by this. Is it okay? It's a parallel systems. So, what you have 1 minus R square to a square. So, it's a low level redundancy. So, ultimately you simplify this. So, this will be your reliability for the low level, and for the high level redundancy, system's reliability is given by 1 minus R square equals to this one. Is it okay? So, this is 2 to the power 2 into R square minus R to the power square. Okay. Comparing the both equations, it can be shown that the reliability of the low level redundancy is greater than the reliability of the high level redundancy. Is clear? So, R low minus R high is equals to, ultimately you have these expressions in this particular case. Is it okay? So, this way you compute, that means you try with first high level redundancy, and again you try with low level redundancy, okay, and then you compare, okay. So, which particular system is having the higher reliability, so you opt for that one. Is it okay? But only thing is, you make sure that there may be the high level redundancy, there may be low level redundancy, but make sure that whatever the system you have proposed, it is cost effective. Is it okay? At what cost? So, high level versus low level redundancy, when you refer to, so you have these expressions, the final expressions, and it should be greater than equals to 0. Make sure. Is it okay? The difference is greater than equals to 0. That means there is, when you move from say high level to low level, is it okay? Or you move from say low level to high level, is it okay? When the exact values of the component reliabilities are known, it's okay. So, if you find this is greater than equal to 0, obviously you opt for low level redundancy. Otherwise, you will opt for high level redundancy for the time being. Equality obtained when R equals to 1. This is true if the components reliabilities are mutually independent. That assumptions we are making. Is it okay? There could be relaxation of this assumption. That means these independence conditions may not be valid or may not be true. So, but here at the initial stage, as a first approximations for the given systems, we are assuming that the components reliabilities are mutually independent and independent of the configuration. That is very important in which they are placed. Is it okay? This is the basic assumptions we make. Both the low level and the high level redundant systems will fail if either both components A fail or both components B fail. Is it okay? So, whenever you create a configuration, when you create a systems and you look at the systems from say the reliability perspectives, now you must know that under what conditions the systems will fail altogether completely. Is it okay? So, that conditions you should be aware of, and normally we go to the component level. Okay, so the system fails because the component, a particular component or a group of the components fail at a particular point in time. So, under what conditions they may fail, so you must be aware of. High level redundant systems can also fail if one A fails and one B fails, as long as they fail on separate paths. Is it okay? So, this is the condition, so you must know. So, you must study minutely the configuration of a system. Is it okay? Whether it is with low level redundancy or high level redundancy or no redundancy at all, and then you need to list down the conditions, okay, in which the system may fail. Hence, the high level redundancy systems has additional failure paths. Okay, so after we consider this, now what you need to know at this level, because we have covered many aspects of reliability modeling. Now, at this point in time, you must know that how many different ways you can improve the reliability of a system. Is it okay? Now, obviously, you know what we are assuming, that the system reliability depends on the component reliability. So, if the component reliability is poor, whether you opt for a series configuration or say the series structure or parallel configuration or parallel structures or a combination of both, or say you opt for the systems with redundant components or say the standby components, you cannot assure high reliability for the systems. That means the component reliability you can improve. So, and as you might have noticed that if you deal with more number of components, like say in a particular case, like say is a missile system, is having some around say 2000 components, and most of these components are in series. So, what you need to do, that means through redesign approach, whether from the reliability point of view, whether you can reduce the number of components in the redesigned system. So, the first option is you have to think of ways and means, okay, you have to think of approaches, okay, with which you can decrease the number of components. Is it okay? So, even if you decrease, even if it is a series system, if you reduce the number of components, you will find that the system reliability may improve. So, that is the first option you have to explore. There are many cases, the design improvement project, we opt for this one. Is it okay? Under one option could be that instead of having two components, why don't you have say a combined component? Under certain conditions you can combine them, under certain other conditions you cannot combine. Is it okay? So, those details when we discuss the cases, when you discuss numerical problems, so we will be referring to those alternatives. Second option is using better quality materials. That means you just look at the physical property, the chemical composition of the materials, okay, which you use in designing the component. Is it okay? So always there is an improvement possible. It is a better quality material you can use. So that option always you try. Is it okay? So this is another option. And normally, whenever we talk about the reliability improvement, we say that we must believe in the concept of design for reliability. That means even at the design stage, you already aware of, say, what are the the steps or what are the activities you need to carry out during the product development stage. So the design stage. So using better quality materials, improving the reliability of the individual components. Is it okay? Changing the configuration. That means from the series, can you change it to parallel? Is it okay? If it is parallel, can you move from say parallel to parallel with say the standby components? So there are many options. Using standby components, I have already mentioned that how to improve the reliability. And the last one is using the principle of derating. That means suppose you say that the spindle speed is 500 rpm. Is it okay? So that's the maximum one. Now if you can run it with say 300 rpm, obviously your production rate may be affected, but the reliability of the systems will improve. So there are many cases where you say that if I start working with the process with the the highest levels of the process parameters, okay, the risk may be very high. That means okay, the performance, the quality of the item which you are producing may be very high, but there is a risk of it's a failure of the systems also could be high. So in those cases, these principles of derating we always apply. Now here is just one example I will just go through. Like say find the reliability of a standby system shown in figure. Already the figures are shown with one basic component and two standby components. That means n equals to 2, and we are assuming that exponential time to failure distribution. So you just refer to this particular problem, just go through the failure rate for each component, each having an exponential time to failure distribution. The failure rate for each component is 0.004 per hour, and the period of operation is 300 hours. Is it okay? Always the time is to be mentioned for computing reliability. What is the mean time to failure? Now if alternatively if you go for 3 components in parallel, that sort of system, what is the reliability of the system? So what is the mean time to failure? So this too we have just applied the formula. Like you apply the formula with these values, you get the system reliability as e to the power minus lambda t into 1 plus lambda t plus lambda t square by factorial 2. So this is 0.879. Next one is the mean time to failure n plus 1 by lambda, that is 750 hours. And if the system has all 3 components in parallel, obviously F1 is 1 minus e to the power minus lambda t, and the system's reliability will be 1 minus 1 upon this one, that means 0.6988 to the power 3. Is it okay? So 0.659. So always you will find that equivalent parallel system will have less reliability, and the mean time to failure for the parallel systems we have already we know that this is the expression for MTTF. Is it okay? 1 upon lambda 1 plus 1 upon 2 plus 1 upon 3. Is it okay? So this value is 458.33 hours. So note that the system reliability and MTTF of the standby and parallel systems differ significantly. So here we stop. So we conclude this one. You can refer to this particular reference textbooks.